Someone asked me to make a video on Laplace transform, so I'm going to be using this problem to explain what it is about. Really, Laplace transform, like I said, is not as difficult as it may sound. The only major challenge that you need to undergo is that you need to know about the you need to know the table, be familiar with the table, different transformation. Okay, when you take the Laplace transform of this type of function, what does it give you, and all of those things. Once you are done with that, every other thing is just complex algebra. And no matter if you have to do Laplace transform, then no matter what the algebra is, it cannot be too complex for you. So this is an initial value problem. Why is it an initial value problem? Because we were given the initial conditions that the value of y when t equals to 0 is 1, and then the value of the first derivative of y when t equals to 0 is 3 as well. So that is why it is called an initial value problem. So let's quickly look at it. So the first thing you want to do is that it's just like, let's say I'm trying to solve a particular equation. Let's say the equation I'm trying to solve is, let's say, x over 2 plus 4 equals 5. If I want to solve a problem like this, to get rid of this denominator, what I would do is I can multiply both sides. I can multiply it by 2. So I will multiply this thing by 2. If I do that, I can get rid of 2 from the denominator. So that's exactly one of the things that we're going to be doing in this particular place as well. So we are going to be applying Laplace operator to both sides of the equation. So as you can see, I've written it here. First, we take the Laplace transform of both sides. So you take the Laplace transform of everything here, then you take the Laplace transform of everything on the right hand side. We are still going to use the initial condition very soon. So let's move forward. So this is me taking the Laplace transform. Now, the Laplace transform, the thing about Laplace of sum is the same thing as sum of Laplace. What do I mean by that is that if you have something being added together, subtraction is also a sum, just that you're adding a negative thing. So when you are taking a Laplace of several things that are being added together, it is also the same thing as the Laplace of those things being, you take the Laplace of those things separately and then you add them together. So now Laplace of y prime prime minus 2y prime plus y is then separate Laplace of y prime prime minus Laplace of 2y prime, but 2 is a constant, so you can easily bring it out, and that is how you see this distributed. So on the right hand side as well, cos t minus sin t, it is also distributed. So when you move forward, now this is where the whole thing now starts. You see, for the Laplace transform, there are certain, like I said, that you need to know the table. You need to be familiar with the table or how this thing works and blah blah blah. You see, when you take the Laplace transform of y prime prime, then this is going to be s squared y of s minus s y of. So this is a standard thing. So you don't need to ask, oh, why did I get it? This is a standard thing. So this right here is the Laplace of y prime prime. Just go to Google and check for standard table of Laplace. You will be able to like get all these things. For y prime as well, this is this right here. Yeah, this right here is the Laplace transform of y prime, and Laplace transform of y is just y of s. So I've taken care of the left hand side. For the right hand side, Laplace transform of cosine is s over s squared plus 1, and that of sine is 1 over s squared plus 1. When you solve this, you get s minus 1 over s squared plus 1. So I think I've put a note here as well. So moving forward, then you have so all what we need to be doing now is to simplify this guy, because and what are we going to be solving for? We are solving for, this is what we are solving for, y of s. So you know you can do your algebra. So this will then be s squared y of s, that is opening the this thing up, minus s of. Now the reason why this y of 0 has become 1 is because the initial conditions were given. So y of 0 is 1 and y prime of 0 equals 3. Somebody could ask that, oh, what if the initial condition was not given? Just represent them with an arbitrary constant. So for instance, if it was not given, instead of writing 1 here, I could write k1, and then for y prime, for the value of y, which is 3 here. So if you can see here, y prime of 0, which is 3 here. So you can represent that with k2. So y of 0 can be represented with, so instead of this initial condition y of 0 being 1, you can represent it with k1, and you can represent y prime of 0 with k2. So they are just arbitrary constant. That is, if it is not an initial value problem, you don't need to fret. So all I'm just doing out here is that my work starts from this side. I'm substituting. So I've been able to simplify all of this now. S squared y of s minus s times y of 0 is 1 minus 3. Then minus, we have these two are here. S times y of s minus y of 0 is 1. You know that, plus y of s equals this, which is s minus 1 over s squared plus 1. So what do we have to do is just basic simplification. As you can see here, s squared y of s minus 3 minus, blah, blah, blah. Then from here, you see that y of s is here, y of s is here, and y of s is here. So all I did was that I factorized that. So this is s squared minus 2s, then plus 1. So then we have left here minus s minus 3 and plus 2. And when you do all of that, you have minus s minus 1. This right hand side still remains what it is. Then don't forget I told you that what we are solving for is this y of s itself. So in the bit to do that, we take everything to the right hand side. So minus s minus 1 goes to the right hand side, that's plus s plus 1. So when you do that simplification, the LCM is s squared plus 1. Then, you do your expansion. So we have s minus 1 plus s cubed plus s squared. That is, when you take the LCM, this is 1. You take the LCM. If you're taking Laplace transform, this should not be a problem for you. So the next thing is that since we have gotten that right hand side, let's divide through by this guy. So dividing now by this guy, so we have y of s equals this. So if y of s equals to this, one thing we want to do is that this is not really like the desired thing that we want. So we want to resolve this thing into partial fraction. So resolving into partial fraction, you should know how to do that. So we have a quadratic term and we have a repeated linear. So for the quadratic term, we are using a linear numerator, and for the repeated linear, we are using a constant numerator c and d, but just do it in that form. So I believe that anybody that is doing this knows what partial fraction is about already. So then you do your blah 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 partial fraction. So what we're doing is we are trying to solve for this constant a, b, and blah blah blah. So with all the, if you don't know how to solve partial fraction, you can let me know in the comment section. I will make a video on how you solve partial fraction as well. So yeah, so I got the value for my a. So doing all of these things, you get the value. So I got the value for a, I got the value for b, I got the value for c, I got the value for d. So this is a, this is d, this is a, and this is c. And then I got the value for b as well. B was negative 1 over 2. So now substituting that into all of these, when you simplify all of that, so you get this reduced. So hence, it implies that our y of s is given as this. But why do we actually have to take the what's it called now? Resolve into partial fraction is because this is not, this y of s is the Laplace transform. If you go back to this, to the way I said, y of s is a Laplace transform. But what we are solving for itself is this y of t. That is the solution to the differential equation. So getting y of s in the form that we got before we started resolving. So getting y of s in this form, it is not going to be easy for us to find the inverse Laplace transform, because there's a table and then we have standard Laplace transforms. So we won't be able to get the actual inverse from here. So that is why we have to resolve into partial fraction. So with this partial fraction now, so if you look at it here, this is what we are able to get. So to do the inverse Laplace transform, what we just have to do is that what? We take the, just like we did Laplace transform earlier, Laplace transform of sum is the same thing as sum of Laplace transforms. So in this place as well, the inverse Laplace transform of sum will also be the same thing as the sum of inverse Laplace transforms. So take the inverse Laplace transform. Of course, you know that when you take the inverse of this one, it will give you y of t, which is what we are solving for. Then the inverse Laplace transform spread it through this guy. So this is supposed to have the inverse symbol. So if you go through this place now, I had to like split it as s over s squared plus 1 plus 1 over s squared plus 1, then plus 3 over 2, 1 over s minus 1, and yada 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 like that. So all of these are, you're going to find them in the table. Like I said, the major thing that is going to be challenging is being familiar with what is there in the table, not really like the actual thing. So then you just be taking the inverse Laplace transform. This is for this, this is for this, this is for this, and this is for this. So when you're done with that, just tidy it up, and then you are all done, and that's it. So you can see how Laplace transform is very, very sweet, and then it made life so easy for us. We're able to solve for the solution. So if you have, maybe let's say you have your own problem, um, you can drop it in the comment section. I think it's a good thing that you can now snap. You can put image in the comment section. So put your own problem. I can solve it and then make a video and go through it with you as well. So I guess I'll see you in the next one.